Okay, hello everyone. Um, in this movie clip, as I told you in the previous movie clip, we are going to learn what the depletion approximation is. So basically, on the right hand side, you can see the energy band diagram of MS contact at thermal equilibrium since the Fermi energy level is single valued. In other words, along y-axis in the energy band diagram indicates the energy of electron, and now the Fermi energy level is a single valued. So we can guess that this energy band diagram has been drawn at thermal equilibrium. Okay, so last week, sorry, last week we have learned how two separated systems, such as metal and semiconductor, when they are combined together physically, what will be happened when we building up and drawing up the energy band diagram of physically combined MS contact. So while we are developing and understanding how to draw the energy band diagram of MS contact, we put our eyes on the band bending at the interface of MS contact. Some student would have this kind of question: how come the energy band bending has been over at this point, at this specific point, say x of xn, because this is a semiconductor n type, so I use the subscript n. So how come the energy band bending has been finished at the x of xn? Why is that? There is no exact point, I mean the ending point of the band bending in MS contact. It's a smoothly, the band bending, the degree of bending should be smoothly uh, removed. But in this energy band diagram, as you can see here, the band bending has been over sharply at x of xn. This is the main concept of depletion approximation. Okay, so in other words, this is an n-type semiconductor, so there are many donor atoms here and there. If I uniformly dope this semiconductor, we can claim that the dopant atoms are uniformly distributed out in this, especially at the surface or near the interface of MS contact. Okay, then at x of xn, so in this range of in between x of 0 and x of xn, all the dopant atoms are ionized, and its partner, I would say the electron, the fifth electron of this donor atom, has been diffused into the matter side or into the bulk side. So the only thing left behind is tightly bonded ionized donor atoms. You know why donor atoms are tight, cannot be moved in the semiconductor? As I have just drawn, four neighboring silicon atoms are tightly binding a single ionized dopant atom. So that is the main reason why the donor atoms can never be moved once it is electrically activated, I would say. Electrically activated means, a certain silicon atom has been replaced with the donor, and it is well bonded with the four neighboring silicon atoms. Afterwards, the donor's atom, coming from the column 5 in periodic table, has a fifth total 5 outermost electrons. 4 out of 5 electrons would be used to complete and build up the covalent bonds with the four neighboring silicon atoms. However, the extra one has been left. So at thermal equilibrium, or at room temperature at 300 Kelvin, the binding energy between, fifth outermost electron and the donor atom can be it can become loose, so that the fifth electron can be freed out, becomes free. Okay, this mechanism, this event would be happened across the silicon material. But as we have learned, when matter is contacted with semiconductor at the interface, many electrons are diffused out, so that electron is depleted out near the interface of MS contact. Then the next question is, in what area all the electrons are depleted out? Can we define the sharp edge of the region where the no electron is available? Yes, we can do that, even though it is not allowed physically, but we can do that. How? We can have our own approximation or our own assumption. That is named as depletion approximation. So the depletion approximation said that the semiconductor part in MS contact is depleted of electrons in case of n-type semiconductor, or more generally speaking, the semiconductor, n-type semiconductor or p-type semiconductor, both can be depleted of mobile carriers to a depth of W. Okay, to a depth of W. This is the core part of the depletion approximation. So as shown in this energy band diagram, from the interface down to x of xn, that is defined as W. W is defined as the depletion width of this depletion layer. So depletion approximation said that the semiconductor part is depleted of electrons in case of n-type. Here, no electrons available in this conduction band edges. Okay, to a depth of W. So beyond W, when x is higher than xn, many electrons are available. So here, many electrons are available. You know how those electrons are distributed out as a function of energy, right? Following the Boltzmann distribution. But in this depletion layer, no electron is available because it is depleted out. Okay, so at x of W or x of xn, below, when x is smaller than xn, no electron. But if x is higher than xn, many electrons. That is not very physical, but just to make our life easier, we can use this very simple depletion approximation. Okay, then this depletion approximation has been widely used when analyzing how electrons and holes are moving and roaming around in a semiconductor, especially in MS diode or PN junction diode. Okay, all right, so now let's get in more details. In the depletion region, in other mathematically, if x is higher than 0 and less than W, so from here to here, here the author would like to derive the equation for rho. The meaning of rho is charge density, okay, in the unit of Coulomb per cubic centimeter. How to write up the equation for charge density in the depleted region? The here. Without any specific comments and specialized comments, we can basically assume that the semiconductor is uniformly doped with donors. Okay, so the uniformly doped means ND of X is simply the constant value. Okay, but this n-type semiconductor region can be formed onto the p-type substrate usually, right? So donors and acceptors are mixed up together, but donor's concentration must be higher than the acceptor's concentration because this is n-type semiconductor. So Nd minus Na indicates net doping concentration. Net doping concentration. So if you think of the unit of this Nd minus Na, that means a number of donors or atoms divided by what? Yes, cubic centimeter. But on the left hand side, we need this unit. But on the right hand side, we have this. So what else should be multiplied with this unit? Yes, Coulomb over number. So what is this? Coulomb per number. Yes, unit charge. Okay, so small q, that is 1.6 times 10 to the minus 19 per coulomb per unit, right? I mean, the single electron would have unit charge. How much charge does single electron have? The answer is unit charge. Okay, so 1.6 times 10 to the minus 19. Okay, q. So by multiplying q with net doping concentration, so we're gonna get this Coulomb over cubic centimeter, which is identical to the unit on the left hand side. Okay, so based on the depletion approximation, all the dopant atoms are ionized and all free electrons are depleted out in the range of x of 0 to x of xn. So in this specific region, the charge density can be originated only from the ionized donors and acceptors atoms. Okay, so we can write up this equation. If x is in between here. Okay. Then the next one is beyond the depleted region. In other words, if x is higher than xn, or you can use a w because w indicates the width of the depletion layer of MS contact. So if x is higher than w or xn, what is a charge density? So I'm talking about here. In this bulk region of MS contact, what is charge density? Maybe not long time ago, a few weeks ago, or maybe in the first half of this lecture in this semester, the charge density of semiconductor can be written as this: Q times P minus N plus ND minus NA. You can look for the slide showing this equation. Okay, if in N-type silicon material, N is more dominant than the hole concentration, so you can ignore this p-value. And the donors and acceptors would be mixed up together in N-type silicon material because basically it is p-type silicon substrate, and you can inject many donor atoms so that the net doping concentration is defined as Nd minus Na instead of simply Nd only, right? So using this equation, okay, you can write down the charge density in the beyond the depletion layer. So Q times P minus N plus ND minus N. But P is much smaller than N, you can ignore it. And now ND minus Na. But this is N-type, so donor must be higher than Na, so you can ignore it. Then the two terms are left, minus N plus ND. But as you know, in N-type semiconductor, the electron concentration is governed and controlled by donor's concentration. So at room temperature, all the donors are ionized so that this equation is always true. So instead of ND, you plug in N. Then minus N plus N are cancelled out together. So in the end, charge density is 0. Okay? As written here. So in bulk n-type silicon material, the charge density is zero. In other words, it is neutral. Okay, again, it is neutral. In other words, the charge density is zero. Okay. Okay, so we got two equations depending on the X in MS diode. Now let's draw the charge density plot. Okay, charge density plot, which means rho versus X. Let's draw it. Here, y-axis indicates rho, x-axis indicates just a position or displacement of MS contact, and here is the inner phase at x of 0. As we have just learned, between 0 and W, this area is named as depletion region. Okay, so in the depletion region, the charge density is determined by donors and acceptors concentration. So simply speaking, we can ignore the n sub a because this is an n-type, so ND must be much higher than n sub a. In my lecture, I said if ND is much higher than NA, which is identical to the sentence that ND is 10 times higher than the NA. Okay, so suppose that NA is 10 to the 16 and ND is 10 to the 17, then you can ignore this value. Okay, so simply Q times ND in the depletion region. So here you can see that plus Q times N sub D, and that is very constant as a function. As X is varied, Q times ND is constant. Why is that? Because we assume that the semiconductor is uniformly doped, okay? And X of W, or when Xn is equal to W, then charge density is abruptly switched to the zero value. Why is that? That is not really happened. That is not physical at all. But we have adopted to use a depletion approximation. The depletion approximation said at x of w, if x is lower than w, no free electrons. But if x is higher than w, I mean the in bulk region, there are many electrons available. So the bulk region is very neutral. Okay, so in other words, charge density is zero. So mathematically, the step function should be used to describe this charge density plot. Okay, just for your information, let me draw the real exact exact solution to draw the charge density plot. So if I use very complicated mathematical models, so you're gonna get this curve shape in rho versus x. But this area, missed area, would be matched to this area. 1, 2. Total area is identical. So maybe there are very complicated equation to derive this equation, but I don't want to go over it. Just in case, I'm mentioning that this exact solution is kind of redundant when it comes to hand analysis of MS contact. But when it comes to the computationally intensive uh, FEM fine element method, then you should consider take into account a very complicated equation to do the hands-on analysis. But I don't want to take care of it in this lecture. Okay, so just for your information, this step-like function is not real, but the real one is should follow this smoothly modified curvy shape in rho versus x. Okay, so again, in summary here, that you should understand and you should define what the depletion approximation is. Okay. All right, now let's move on to the next slide, and we're gonna do electrostatics analysis. Okay, I said we're gonna begin the analysis of electrostatics. So what is electrostatics? Think about it. What is it? In device physics, when it comes to the electrostatics, you should come up with those four variables in your mind. Rho, charge density, and then electric field, and then potential or voltage difference, and energy of electron. So let me write down the unit for each variable. Coulomb per cubic centimeter, and that is volt per centimeter, that is volt, that is electron volt, which is identical to, just for your info, 1 electron volt is identical to the 1.6 times 10 to the minus 19 joule. Okay, so familiarize yourself with those four variables. Whenever we are saying that I'm doing the I would like to know the electrostatics of my device, which means you would like to know those four variables: rho, charge density; E, electric field; V, potential; E, energy of electrons. And notice that those four variables are closely associated to each other. How? The first, rho and E, are closely associated to each other throughout the Poisson's equation. So in electromagnetic class, EM class, you have learned that Poisson's equation or Gauss's law. I have explained it in this lecture as well. So it turned out that the electric field variation with respect to x is proportional to what? Yes, charge density. And the coefficient is defined as 1 over dielectric constant. Since we are talking about the semiconductor or silicon, I have used the subscript of Si or silicon. Okay. So we can use this equation, Poisson's equation, dE dx is equal to rho over epsilon silicon. On the right hand side, you can see that the charge density plot. Okay. One thing I forgot to mention in the last slide is this delta function. What is this? Now we have a MS contact, and we put our focus on the semiconducting part. However, take a look at the metal side as well. If positive charges are existing in the range between x of 0 and x of w, from 0 to w, there are many positively charged particles. This MS contact should be neutral overall. Therefore, at some point, negative charge should be existing and canceling out this positive charge, the total amount of positive charge. But intuitively, you have already known that the matter has many electrons, tons of electrons. Because of that, metal is very very conductive. It can flow much current flow. So once positively charged particle, which is actually the ionized donor atoms, between 0 to W, right? I'm using the depletion approximation. So many electrons would like to move toward the interface at x of 0. And many electrons would form a certain layer. However, this thickness is much thinner than the depletion layer's thickness. So mathematically, we can use a delta function. In other words, this area is supposed at 1, then the height of this arrow is 1, and the width value is, almost 0. Okay, so using delta function, we can complete the charge density plot. Then now, let's do the analysis, electrostatic analysis. So the very first step is to know and to derive the equation for electric field as a function of x. Notice that all the analysis has been done in one dimension. Okay, even though MS contact should be formed as three-dimensionally, but we only think of how electrons and donors are ionized and how the depletion regions are formed. Everything is discussed along the x direction only. We are not talking about the y direction and z direction, because along the y and along the z direction, everything is identical. Depending on the x value, something is different. Okay, so now let's solve this first order differential equation. So you can do that. So in this depletion region, the rho has been defined as Q times n sub d, right? So just plug in the Q times nd into the rho, then you're gonna get, so this is electric field. So dE dx is equal to Q times nd over epsilon silicon. So you can solve this first order derivative equation. Very simple. So from this first order derivative equation, Q times nd over epsilon s x plus certain value. Okay, then we should figure out what the C is. Then what else do we need to know the value of C? Yes, boundary condition. So going back to the charge density plot here, what is the boundary condition? Yes, when X is W, the electric the electric field should be 0. In other words, in this regime from x of 0 to x of w, the electric field is not 0. Otherwise, electric field is 0. Going back to the, if I go back to the previous slide, all of my notes I have done in this slide would be lost, just in case. Yeah, in the previous slide, you may see that you made this energy band diagram, right? So at x is w, the band diagram is very flat. So flat means conduction band edge. Flat means dEc over dx is 0. But as we have learned, dEc over dx is equal to Q times electric field. So if this value is 0, Q is non-zero, so electric field should be 0. So in other words, in the bulk region, I'm talking about this area, right? When x is higher than x of n, right? The electric field is 0. So we can use this boundary condition. If when x is w, Ex is 0. So plug in the w here, and that is w and total value is 0. Then C is what? Minus Q and D over epsilon s w. Okay. Then plug in again. Back to the original equation, then you're gonna get this solution. Okay. All right. So let me see. We have finished this analysis, part of the electrostatic analysis. Next one is this guy. E versus volt potential. So you remember this equation. The electric field is defined as potential difference. Okay, so when here is x of 0, here is x of d, and here the potential value is high and this is low, I mean the plus and minus. Then electric field is formed from plus to minus, right? Then using a first order derivative equation, you can write down this. V final minus V initial divided by final destination, I mean the x final minus x initial, is defined as electric field. But we should double check this equation is valid and very physically describe these events. So V final is V low, right? And V initial, the voltage at the initial stage here is VH. And X final is defined as D, and X initial is 0. So if I write down it again, VL minus VH divided by D minus 0 is equal to electric field. But now electric field is formed along the plus X direction, so this value should be positive. But take a look at the left-hand side. VL it must be smaller, lower than VH, so that is negative. But D is higher than 0, so that is positive. So left-hand side is negative, right-hand side is positive. That doesn't make sense. So to mathematically make it valid, we need one more thing, that is minus sign on the right-hand side. Okay. So we got this equation, dV dx is equal to minus the electric field, minus E. From the equation above, here, electric field, you can plug in here. Then you can get potential as a function of x if you can solve this first order derivative equation. Okay. So this first order derivative equation is identical to the Vx is equal to minus electric field dx. Of course, this electric field is the function of x. So I have right down here dEx dx, but all right. Then now you can solve by yourself, I guess. Instead of x, I have used x prime because here x prime is the variable when solving this integration, but the final values should be associated with the x itself. Anyhow, so plug in the equation Ex in the previous slide into this into this term and solve it, then you're gonna get this value. But you need one more thing to completely solve the first order derivative equation. What is it? Yes, as I have previously told you, the boundary condition is necessary. Then what is the what is the required boundary condition for this? Yes, on the right hand side you can find it. Electric field at x of w is 0. Okay. Previously we have used the rho at x of w is 0. You can use another boundary condition here as described here. Then you're gonna get this second order polynomial equation for v as a function of x. Okay. Then another thing that I want to tell you is this. Yep. Potential. So now we have done rho as a function of x and electric field as a function of x. You can see that this. Just one more thing. This slope is very associated with doping concentration, right? So doping concentration can decide how the electric field is varying. Okay, so definitely electric field is formed along the minus x direction, and the electric field is very strong and peak at x of 0. In other words, at the inner face of MS contact, the electric field intensity is maximized, and it is degrading and decreasing, but at a linear pace, not exponential pace, not at nonlinear pace. Exactly at the linear pace, the electric field has been varied and decreased down to the depletion region's edge, where x is W, and the slope is very dependent of doping concentration. So suppose that your doping concentration of semiconductor part has been increased, then can you guess the electric field versus X plot? Yes, it would become like that. So with a higher doping concentration in the semiconductor, the depletion width would becomes narrow, and the peak electric field intensity has been intensified more. Okay, all right, and that's all for the EX and rho X. And the next one is potential. I guess we have lost all the notes. Yeah. Anyhow, when it comes to the electrostatic analysis, rho, electric field, and voltage, potential, and energy of electrons. So now it's time to understand the potential. We got this value equation, and the one thing that I want to define is this: at x of 0, the potential value V is defined as a this minus times minus VBI. So this VBI is defined as built-in potential. Basically, this built-in potential means this voltage difference or potential has not been supplied and obtained from outside. Going back to the energy band diagram for the MS contact, we didn't apply any voltage across the MS contact. But in the depletion region, there is electric field. Why is that? What is the physical origin of the built-in electric field formed in the depletion region? Yes, doping, donors. Because donor atoms has one more electron compared against the silicon atom. So donor atom would become ionized. In other words, it's going to lose its fifth electron. However, the ionized dopant atoms are tightly bonded with the four neighboring silicon atoms, so it cannot be moved at all. But electrons coming from the donor atom can become movable. So once that n-type semiconductor is combined with a metal system, resulting in the MS contact, because of the work function difference. In other words, because the Fermi energy level of metal system and semiconductor system is very different, so that the movable electrons would be swept away from the inner face of MS contact. However, the ionized dopant atoms are left behind. In other words, the silicon atoms can tightly binding the ionized dopant atoms. This is the main mechanism how come the electric field in the depletion layer has been formed internally. So we can say it as built-in electric field. But just a moment ago, I mentioned that the electric field can be defined as the potential difference or voltage difference for a given region. So in this specific MS contact, in the depletion rate region between X of 0 and X of W, the potential difference should be there because built-in electric field has already been formed. So that voltage difference is defined and understood as built-in potential, denoted as V sub Bi. Okay, so we can draw the potential plot V versus X across the MS contact. So we should define that when X is W, I mean at the edge of the depletion layer is 0. That is reference value. I have decided to use 0 value or reference value at X of W at the edge of the depletion layer. Then at X of 0, at the interface of the MS contact, a certain amount of potential, non-zero potential value should be there. How to define it? Yes, built-in potential. So we can use built-in potential. But this electric field intensity is negative. So uh, in this direction, electric field is formed. So potential, the highest potential point is here, V high, and here is V low. So I have used the minus sign. Okay. So now you can plug in x of 0 here and x is 0, then this value is equal to minus VBI. Then you're gonna get W value. So W, depletion layer, depletion width of depleted layer width W can be expressed with this equation. So take a look at what terms are used for W. Yes, VBI, N sub D, Q, dielectric constant. So because we are sticking on the semiconductor material silicon, so epsilon, Q, those are the kind of constant, and VBI, N sub D kind of a variable. So with a higher doping concentration, the depletion layer width becomes narrow and narrow. Okay, and this VBI, we're gonna learn that later, but VBI is actually the function of donors and acceptors concentration. So in conclusion, the doping concentration in semiconductor is the key knob in determining the depleted layer width. Okay, so on the right, on the bottom side, you can see that W depleted layer width decreases with increasing N sub D. Okay, so we have a 2 MS contact sample, and here doping concentration ND is 10 to the 16, and here N sub D is 10 to the 18. This is sample number 1. This is sample number 2. Which sample would have a wider depletion layer? Which sample would have a narrower depleted layer width? You can answer it. Okay. All right. That's all for the lecture note. This and in the next movie clip, I'm going to explain the current versus voltage characteristic of MS contact. So see you in the next movie clip.